At 7:34 on a Monday morning, a man standing inside the terminal at Pereira Airport had his phone out because he was streaming to his followers. Ordinary morning, ordinary arrivals hall. A few seconds later, he was underneath a table, still filming, while pieces of the ceiling came down around him. That footage was around the world inside an hour, so was the rest of it. A family in Pereira crowded into their bathroom doorway. A 6-month-old baby lifted out from underneath 5 collapsed stories in Cali. A line of strangers passing broken concrete hand to hand down a street that had been a street the day before. By the second morning, the death toll was in the hundreds and still climbing. More than 1,000 injured, thousands more unaccounted for. Colombia declared a national emergency, and a president who had been sworn into office days earlier found himself standing in the wreckage of the country's coffee region on what was effectively his first working week. All of that was reported. All of that made the news. What did not make the news is the strangest fact about this earthquake, and it is genuinely strange. Not strange in the way headlines mean it. The rock that broke should not have been able to break, not wasn't expected to, not hadn't in living memory. Rock at that depth, at that temperature, in that specific position beneath Colombia, should not be capable of producing an earthquake at all. It should bend, it should creep, it should soak up strain and let it go slowly and silently across centuries, the way warm wax does when you lean on it. Instead, it snapped, and 68 miles above it, cities came down. This is where that earthquake actually came from. To understand why this earthquake behaved the way it did, you first have to understand how it felt, because how it felt is the first piece of evidence. It struck at 7:34 in the morning, which in the coffee region means school buses, delivery vans, morning shift. The epicenter was around 20 kilometers from a town called San José del Palmar in the department of Cauca, a densely forested mountainous stretch of western Colombia that is one of the wettest places on earth and one of the least connected to the rest of the country. The shaking lasted somewhere between 90 seconds and 2 full minutes. Sit with that number for a second. Most destructive earthquakes are over in 15 to 30 seconds. 90 seconds is long enough to wake up, understand what is happening, wake somebody else, argue about whether to run, and still be inside the building. And it was felt by something in the order of 34 million people across 4 countries. Bogota felt it. Medellin felt it. It carried into Ecuador and Panama and Venezuela. But here's the detail that ought to stop you, and it is the thread we are going to pull for the rest of this video. Most of those 34 million people did not describe violent shaking. They described rolling, swaying, a long, slow, sickening motion, like the floor had become the deck of a ship. Buildings in Bogota moved gently for a minute and a half and then stopped, and everybody went outside and stood in the street, and nothing had fallen down. A magnitude 7.4 that rolls. That is not normal. The magnitude scale is logarithmic, which means the steps in it are much bigger than they look. A 7.4 is not slightly worse than a 6.4. It releases something on the order of 30 times more energy. On any normal reckoning, a 7.4 is filed under catastrophic, the kind of number that, in the wrong place, ends a city. This one released all of that energy and then delivered it to 34 million people as a queasy, drawn-out sway that most of them stood through. And in a handful of cities, that same rolling motion took buildings apart. The epicenter of this earthquake was near a town of roughly 5,000 people. 2 days after it struck, rescue teams still had not reached it. Chaco is that isolated, mountains, rainforest, few roads, and a rainy season that turns the few roads there are into something you cannot drive a crane down. Whatever happened directly above the rupture, the country largely did not know yet. Meanwhile, the dead were being counted 150 miles away. Pereira, Cali, Manizales, cities in the coffee axis, and the Cauca Valley, well outside anything you would draw as a damage zone. Cali is Colombia's 3rd largest city and sits roughly 280 kilometers from where the ground broke. It lost dozens of people in 90 seconds. Buildings collapsed. A hospital was damaged badly enough that patients had to be evacuated, and a pediatric wing was compromised. 16 people were left hanging in an aerial cable car above Pereira for 6 hours. A terminal building at Pereira's airport failed. Airports across the region suspended operations. 5 capital cities went to red alert. It is worth saying what the coffee axis actually is, because because the name flattens it. This is a compact, mountainous, intensely cultivated stretch of the central Andes that produces a large share of Colombia's coffee and a disproportionate share of its national identity. It is dense. It is built on slopes and valley floors, and it is one of the most economically consequential pieces of ground the country has. An earthquake that arrived from Cauca, a region on the far side of a mountain range, sparsely populated, barely reachable, landed almost all of its costs there, so the picture is inside out. The place closest to the earthquake was, as far as anyone could tell, quiet and unreachable. The places furthest from it were burying people. There was one more anomaly, and at the time, it read as luck. A magnitude 7.4 on the Pacific margin of South America should have started a tsunami alert on 3 coastlines. It did not. Within about an hour, the Pacific Tsunami Warning Center cleared the entire region. No threat to Colombia, no threat to Ecuador, no threat to Panama. Nobody was evacuated from a single beach, and the reason for that turns out to be exactly the same reason Cali fell down while San José del Palmar sat in silence. The earthquake was too deep. The United States Geological Survey put the rupture at about 110 kilometers down, 68 miles. The Colombian Geological Survey put it at 96. The European Mediterranean Seismological Center came in lower again at 95, with a slightly smaller magnitude. That spread is normal in the first hours of an event. The agencies are working from different station networks, and the numbers converge as data accumulates. But note that even the shallowest of those estimates is deep, astonishingly deep, for something that killed people. Most of the earthquakes that kill people happen in the top 10 or 15 kilometers of the crust. Shallow ruptures put their energy into the surface directly above them, which is why they flatten a defined area and why the damage falls off sharply as you move away from it. Anything between 70 and 300 kilometers down gets a different name. Seismologists call these intermediate depth earthquakes, and they behave according to a completely different set of rules. Energy released that far down has to travel through an enormous volume of rock before it reaches anybody. On the way, it spreads. By the time it arrives at the surface, it has been distributed across a footprint hundreds of kilometers wide, and no single point on that footprint receives the full force of the rupture. That is the trade. Shallow earthquakes hit one place extremely hard. Deep earthquakes hit an entire country moderately hard. It explains all 3 of our anomalies at once. It explains why 34 million people felt it. It explains why most of them felt rolling rather than violence. It explains why there was no tsunami. The rupture was far too deep to shove the seafloor upward, which is the only thing that actually generates a tsunami wave, and it explains the silence at the epicenter, because with a rupture that deep, there is no single spot on the surface that counts as being close to it. Everybody within 400 kilometers was roughly the same distance from the break, which raises the obvious question: if nowhere took the full force, why did anywhere fall down? 2 answers, and they compound each other. The first is duration. A deep earthquake delivers less force, but delivers it for much longer, in long, slow waves. 90 seconds of gentle swaying does something to a concrete frame that 15 seconds of violent jolting does not. It works the joints, cycle after cycle, until something that was holding stops holding. The second is the ground itself. Cali and the coffee region cities sit in valleys on soft sediment. Soft basin sediment does not transmit long, slow waves. It catches them, amplifies them, and rings like a struck bell. 2 cities the same distance from the same earthquake can experience completely different earthquakes, depending on what is underneath them. So, a rupture nobody should have felt strongly became, in a handful of specific valleys, a rupture that took down 86 buildings. That is the mechanics answered. But mechanics is not the mystery. The mystery is what was doing down there in the first place. Off Colombia's Pacific coast, the Nazca Plate is diving eastward underneath South America. It has been doing this for tens of millions of years, and it is why the Andes exist. As that slab descends, it gets squeezed and cooked, and it fractures as it goes. Almost every intermediate depth earthquake on Earth happens inside a descending slab like that one. The slab is cold, it has only just left the ocean floor, geologically speaking, and cold rock is brittle rock, and brittle rock can snap. That is the textbook answer, and for most of Colombia, it is the right one. The country sits at a junction of 3 tectonic plates and has one of the most complicated seismic settings anywhere on the planet. But southern Colombia has something else, something that does not fit. In the Cauca region, there is a cluster of earthquakes occurring at depths of roughly 80 to 160 kilometers, and a subset of them are not happening inside the descending slab at all, They are happening in the wedge of mantle sitting above it. And that is the part that should not be possible. The mantle wedge is the hottest rock in the entire system. It sits directly on top of a plate that has been dragged down into the interior of the Earth, and it is heated from below and from around, and everything we understand about rock mechanics says that at those temperatures, rock does not fracture, it deforms, it flows. Ask it to hold stress, and it will simply yield slowly without ever storing enough energy to release it all at once. An earthquake is, at bottom, rock failing suddenly. Rock that flows cannot fail suddenly. It has nothing to snap. Intermediate depth earthquakes in the mantle above a subducting slab are, in the published literature, described as uncommon, precisely because the mantle there is generally too hot to sustain the kind of failure that produces earthquakes. They happen in Colombia anyway, repeatedly. And on the 10th of August, one of them killed hundreds of people. Colombia is not the only place on Earth doing something like this, and the other example is even more extreme. Under northeastern Colombia, there is a feature called the Bucaramanga nest. It is one of the densest concentrations of intermediate depth seismicity anywhere on the planet. An intensely active zone squeezed into a narrow pocket of rock, roughly 150 to 170 kilometers down. Around half of all the earthquakes in Colombia's catalog are intermediate depth events, and most of those come from that one small volume. It has been studied for decades. The honest position, stated plainly in the research, is that the mechanisms generating this seismicity are not well understood. There are two leading explanations, and they are both stranger than the problem they are trying to solve. The first, water. The idea is called dehydration, embrittlement. When an oceanic plate is formed at a mid-ocean ridge, seawater works its way into the rock and gets chemically bound into the crystal structure of the minerals themselves. Not water sitting in cracks, water locked into the minerals. That plate then spends millions of years crossing an ocean and eventually gets pulled down into the Earth's interior, carrying its water with it. As it descends and heats, those minerals become unstable and start giving the water back. It is released as high-pressure fluid inside solid rock, kilometers beneath anything you would call the surface, and a fluid under enough pressure can force rock apart from the inside. It effectively holds the walls of a fracture open, canceling out the crushing pressure that would otherwise weld everything shut. Rock that was too hot and too compressed to break is suddenly able to break because it is being pried open by water it swallowed at the bottom of an ocean before there were people. The second, a drip. The second explanation is called lithospheric delamination, and it proposes something almost architectural. The idea is that a dense chunk of the base of the continent above becomes unstable and peels away, detaching and sinking down through the hotter, softer mantle underneath it, like a bead of cold syrup falling through warm. Research on the Bucaramanga nest has modeled exactly this, a dense body that has separated and is descending onto the subducting plate below, which in turn drives more fluid out of the slab and concentrates the strain into a small volume of rock. Two mechanisms stacked in the same place. Notice what both theories have in common. Neither of them says the rock is somehow stronger than we thought. Both of them say something else is doing the work. A fluid prying it open or a falling mass forcing the strain. The rock is still too hot to break on its own. It is being made to break. That distinction matters because it means the thing generating these earthquakes is not a fault line in the way most people picture one. There is no crack running through Colombia that you could stand on. There is a process happening inside a volume of rock driven by water that fell into an ocean plate before anything on land could walk, and it produces earthquakes on a schedule nobody has been able to read. Neither explanation is closed. Both are actively argued, and that is the real state of things. There is a zone of the Earth beneath one of Colombia's most populated regions that is capable of generating lethal earthquakes, and the scientific community is still working out precisely how it does it. This is not an academic problem, and the 10th of August is why. When the Colombian Geological Service was asked about historical precedent, they pointed to the 23rd of November, 1979, a magnitude 7.2 in the same broad region. That was the last comparable event 47 years ago. 47 years is longer than most building codes, longer than most careers, and considerably longer than most people's memory of what their own ground is capable of. It is long enough for a city to double in size and fill a valley floor with concrete built to standards written when nobody had felt one of these, and the specific character of these earthquakes makes them uniquely awkward to prepare for. They are rare in any given place. They do not concentrate their damage anywhere you can point to in advance, and they arrive as long, slow waves that a building can survive for 60 seconds and fail in the 90th. You cannot evacuate a region the size of 4 countries. You cannot reinforce every valley. The warning time is effectively 0. What you can do is know the ground is there, not predict it. Nobody can predict it, and anybody selling you an earthquake prediction is selling you something, but But you can build for the specific way this kind of earthquake fails a building, which is slowly by fatigue, or over a minute and a half. That is a different engineering problem from the one most codes are written against, and it is a solvable one. By the second day, dump trucks were queuing to leave Cali. Traffic restrictions were lifted so debris could move. Volunteers with no training were pulling concrete off other people's families in 86-degree heat, and the emergency relief that was pledged was measured in millions, while the damage was going to be measured in something much larger than that. The count of the missing was in the thousands, and the count of the dead had not stopped moving. And underneath all of it, 68 miles down, in rock that our best physics says should have quietly flowed instead of breaking, whatever caused this went back to doing whatever it has been doing since long before there was a Columbia to bury. It will do it again. We do not know when, we do not fully know how, and we do not know how to see it coming. What we know is that it is down there,